Now, welcome. This is our second week. This is the first lecture after the introduction. In the introduction, as you remember, we talked about basically what robotics is, what robots are, what types of robots there are, and how do we classify robots. And as you remember, there was not a single unique classification method, and there were methods of classification according to the geometry, kinematics, workspace, and function of the robots, how it looks. For instance, if it looks like a human being, we were calling them humanoid robots. And today, let's see what we are going to talk about. We start by talking about the robotic tasks. What type of tasks do they carry out? Where do we implement the robots? We implement them for picking and placing something, for following paths, for industrial tasks like welding or spray painting, also for exploration. As you know, for instance, the Mars exploration or moon exploration, especially the mobile robot or hybrid robot, which was sent to Mars, has become really very famous and popular. Also, some delicate works like surgery, even brain surgery, are among the tasks which are carried out by robots. How are they built? They are composed of different components. And here you see a block diagram. It is conventional for engineers to explain rather complicated and sophisticated structures in terms of simplified block diagrams. Here you see a block diagram, a very simplified explanation of the basic architecture of robots. And here you see different components from different fields of engineering. Now, at the brain of it all, there is computer, and there is also controller. This controller can become embedded controller. Robot can control itself. In this type of applications, we call the robots autonomous robots. Or it can be an external controller. If it is an external controller, we need this input device definitely to send commands to the robots. Usually here also we implement hybrid solutions. We like the robot to be autonomous as much as possible, but we like to be able to interfere with it in some tasks when it is necessary. Or this may be to help the robot, to guide the robot, or to stop robot from something dangerous. So this input device sends some commands to the robot, and these commands are directly input into the computer and controller. Robot must sense the environment like us, and the sensors may be very different types of sensors, like visual sensors, audio sensors, or sensors which detect odor, noise, heat, okay, all sorts of different sensors, or proximity to avoid collision. And so we include sensors as a basic building block. And of course, this is all going to be operated by making use of some programs and some data which is already stored. So another block is the storage of the programs and data, and for getting connected to the network. And in many cases, we would like it to be able to be connected to the network. And it is a requirement for us all. At the moment, we carry out this function by getting to the network. Similarly, we would expect the robots to be able to get connected to the network. So this is another important block that we include. There are mechanical parts. After all those functions of sensing and decision making and controlling, in order to get into some action and interaction with the outside world, we need some mechanical parts. So for instance, like a mechanical arm, which resembles the arm of a human being, or more sophisticated arms, depending upon the task the robot is going to undertake. So we must also include this mechanical arm or other mechanical parts, depending upon the functionality of the robot. Of course, when we talk about the arm, we talk about a hand-like structure as well. So we will need the end of arm tooling to be connected to the end of the mechanical arm. And after all these, like us, like any living creature, robots also need energy to carry out some tasks. So we will need, of course, we should not forget the power supply. And therefore, the integration of these all parts, like mechanical arm, sensing, computation, user interface to input devices, and tooling forms, when we combine them all together, we actually can create a robot. So it is a really interdisciplinary system which incorporates many different parts of engineering. We had talked about joints. Joints are part of the mechanical parts of the robots, and these give us the ability to move, to articulate certain movements and gestures. And as we mentioned, that they come in two forms. One is a natural form, like we have, also revolute joints. And the second one is a type of joint that we don't have, it is the prismatic joints. And symbolically, we can simplify their representation. These type of symbolic representations can be used in robotic diagrams. We mentioned workspace already in the introduction lecture, and we also told that the workspaces determine the types of workspaces, determine the type of the robot, or rather the robot type, robot design is done in accordance with the workspace we would like to get. Now we are going to mention another thing. Within the workspace, we here make another definition, which is configuration space. Simply, we mention the configuration space as the space of all joints. But I know that this is not very explanatory, and we are going to explain it in detail in today's lectures. What do we mean by configuration space? So far, just keep in mind that it has got something to do with the joints. So the number of joints, the types of joints have a bearing upon the configuration space. But how? Okay, we are going to detail about this. Let us say that we want to just cover a space, a distance. This is this is a one-dimensional space now. Just we want to cover this. How do we cover this? With what type of joints? We said the configuration space is very much related to the joints. Now you see the simplest explanation of this here. Now if our configuration space is going to be involved just moving linearly from one point to another, prismatic joint actually enables us to move like this simply. But can we do it also with revolute joints? Yes. Revolute joints also may actually provide an ability of covering such a distance. And this is just a foretaste of how the joints are related to the configuration space. Robot taxonomy. What do we mean by taxonomy? The terms we use in robotic, or the terms which are particular to the robotic. Like each field has got its own terms. Robotics has got some terms. For instance, we use a term like actuation. Actuation is related to power source. It may be an electric, hydraulic, or pneumatic power source. And when we talk about the geometry, it is related to kinematic structure. So we should talk about what kinematics is. This is a taxonomic term which we need in the field of robotics. And other terms are generated like open chain, closed chain. Also, there are terms borrowed from other fields like control, which are open loop control, closed loop control, and finally, trajectory, continuous path, point to point. These are the taxonomic terms which are used in robotics. And we have got terms related to the performance, accuracy, repeatability, control resolution. And these are the terms which actually tell us something about the performance of robot. Now let us look at a part of robot. That's the wrist of a robot. Now here we see 3 axes and 3 rotations. And we also now see some new terms which are called pitch, roll, and yaw. Now, pitch, roll, and yaw are the terms, again, are new terms, which are borrowed from aerospace engineering. These are the terms which are used basically in describing the motions of an aircraft. And when we talk about rotations, about three basic axes, we talk about these type of movements like yaw, pitch, roll. Now here again, I'm giving you just a foretaste of some of the terms, but today we are going to also look closer to this. And we are also going to have the first taste of the equations which are used in expressing this type of motions. And when we talk about grippers like this, which are connected to the wrist, we must also talk about these three angles of yaw, roll, and pitch. And delicacy, or in carrying out some very delicate, sensitive tasks, this type of definition becomes very important because, for instance, this task shows that we must be delicately handling a bulb without breaking it. Therefore, how do we precisely define this motion to the robot? Okay, then we must, in order to be able to precisely describe this motion to robot, we must be able to precisely explain this motion in terms of some mathematical equation. Mathematical expressions are common knowledge or common language between the engineers all over the world, but it is not a common language only among the engineers. It is also a common language among the engineers and robots. They also understand the mathematical expressions, not in the direct form, but of course we put them into a language, we convert them into a language that they understand better through some programming. Okay. Now we just entered another term here, another new term, which is very important in defining robots. DOF. DOF is a term which is formed by three words: degree of, or degrees of freedom. So here there is a 3 degrees of freedom manipulator, or manipulator is a particular type of robot which looks like a human arm. And when we classified the robot, we mentioned some robots which look like human arms. And for instance, articulated robots were these. And we mentioned that these robots are formed by 3 basic movements. In this case, it is 3 rotational or revolute, 3 rotational movements, which are provided by 3 revolute joints. And we call it a 3 degree of manipulator. So we can see here that there may be a relationship between the word degrees of freedom and the joints, number of joints and types of joints of the robot. And then we are going to later on, when we come to describe kinematics, we are going to say that kinematics is related to the joints and to the lengths and to the geometry of the robot. In how many degrees of freedom robot can move? When we ask this question, we are actually saying in a more plain English, how many basic elementary motions can a robot do? When we talk about 3 degree of robot, we are talking about a robot which can carry out 3 elementary motions. But how these 3 elementary motions are related to the joints, again, let's make this conceptual frame, but we are going to talk more about it. Okay, this is another 3 degree of freedom robot. Of course, this one, here also you are now seeing the symbolic representations of the robots which are seen here. And if you are following actually by attention, close attention, you will see that this does not correspond exactly to this picture. Why? Because we saw this picture last week in the introductory course, and we said, well, this has got 6 joints. But here we have got only 3 joints. Why? Because these 3 joints correspond only to the part which does not include the gripper or hand part. So 3 degrees of freedom comes from here, 3 degrees of freedom. We've just mentioned it, and we know that 3 basic movements come from here, and 3 ones come from here. Let's try to identify each symbol with the corresponding part component in the picture. Now, this one is a revolute joint, so we understand that here robot can rotate. This one is another revolute joint, and we can see it. Well, this one is actually rotating. This one is another revolute joint. Here we see the prismatic joint, and we understand that this one is not a fixed length, but it moves in both directions. It can increase the length or the reach of the robot, or it can decrease it. So we can now see a one-to-one relationship between the symbolic representation and the picture. If you look at the picture alone, it does not give all of this information. I mean, if you close the left-hand side of this slide, you cannot be sure whether this is a fixed part or whether it is able to rotate. But here on the left-hand side, the symbolic representation clarifies this or removes this ambiguity, exactly showing that there is a revolute joint here. Let's try to see the correspondence between these two. Okay, we understand here this one is rotating. Also, this one is rotating because this is also shown by a revolute joint. And here we can see that there's a rod here, there's a part here which can go up and down. How I know it? Sorry, I should come back. How I know it? Because this prismatic joint is clearly shows us that there is a part here which can go down or up. Here again, I understand it can rotate. Okay, this one can rotate. This one can go up and down. And also I can see that this one can go. This part of the arm is not fixed in length, but it can change its length. Or maybe this can move. Can it move? No, because how am I saying that it does not move, but that the arm here moves? Because this Earth-like image shows me that it is fixed here. Okay, so the movement, this linear movement is actually provided by this arm. There is a prismatic joint obviously here, and this arm also can change its length. So rotation, motion, this arm can move up and down, and it can increase or decrease its length. And this is all said to me by this graphical and symbolical representation on the left-hand side. Okay, you can decode this as well. This is basically something like a printer or a scanner, and it has got 3 prismatic joints, and it moves in a Cartesian coordinate system. Okay, these are the workspaces. We had made an introduction, but this is some sort of repetitive slide. And if you look at it, here you can see a 2-link planar robot. A robot which works on a surface. This robot may be working for grinding or painting a surface, a surface, and the surface, to make the things a bit more complicated, surface is not a straight surface, but it has got a curve, and everything, to make the things simple, is confined to a 2-dimensional plane here, or 2-dimensional space, which is a plane here. And if I want to actually do some task in the 2-dimensional space, then I will need 2 degrees of freedom. So that means I will need 2 joints. So somehow, maybe you are starting to sense the relationship between the task and the degrees of freedom for this task and the number of joints we should use to carry out this task. Okay, can I carry out such a task by a 1 degree of freedom robot? When I mean 1 degree of freedom robot is not able to change its length. So for this particular task, I need the robot to be able to change its length because of this curvature, also the angle. So what am I talking about? I am talking 2 basic movements, 2 elementary movements. Linear movement of changing the length and rotational movement of changing the angle. So these are 2 basic motions. What did we say? The number of basic movements is the degrees of freedom. Therefore, to carry out this task, I need 2 degrees of freedom robot. And also we said degrees of freedoms are related to number of joints. Therefore, I need 2 joints to carry out this task. For a more complicated case, I mean, if there was a space now, if there was a third dimension, if I was asking the robot to carry out this task in the third dimension as well, would this robot be sufficient? No, because then the number of elementary motions would be increased to 3. Then I would need a 3 degree of freedom robot, and I would need at least 3 joints. So I am carefully saying, I'm not saying that 3 joints, but at least 3 joints. Let's come back to this example. Can we do this task with a robot with 3 joints? The answer is yes. It's going to be a more expensive robot, okay, but at least then I need for this test 2 degrees of freedom robot, but higher degrees of freedom robots, or robots with higher number of joints can also, of course, readily do this job. But remember, as we increase the number of joints, the kinematics becomes more complicated and the calculations take more time and the robot becomes more expensive. So this is the simplest possible solution for carrying out this task. But robots with higher degrees of freedom can skillfully do this job as well. Here, we entered now another concept or another term into our taxonomy. Moving coordinate frames. In many of the engineering or in electrical engineering and computer engineering works, we did not need this term. In an electronic circuit, you do not need moving coordinates. But when it comes to robotics, there is a need for moving coordinate frames. There is a need term now. Now, we all know from the very beginning that everything is described by first establishing a reference frame. This reference frame is established on a fixed location, somewhere on Earth. Although even Earth is not fixed, for any operations on Earth, it is fixed. But when you go to space, the fixed, Earth fixed frame also becomes a moving coordinate frame. But let's come back to the operations on Earth. Let's come back to operations like industrial robots on Earth. Then any reference frame which is fixed on Earth is called a fixed reference frame. But we also talk about some reference frames which are not fixed on the Earth, but on the robot itself. And you see 2 reference frames like this already. This is reference frame 0, which is fixed, but these ones are moving because where they are fixed are the joints, and as joints move, they are also moving. So we call them the moving coordinate frames or moving reference frame. So we entered now another new term. Now, it is not sufficient in robotics just to talk about reference frames or coordinate frames. We should specify whether they are fixed or they are moving. Okay, so some of the problems we are going to encounter with. For instance, if we know the angles theta 1 and theta 2, can we figure out what x and y are? Well, this is not such a complicated problem at the moment, is it? By using geometry, we can solve it because it is in 2 dimensions, and it involves only 2 types of 2 triangles. Actually, one triangle is here, the other triangle is here. Okay, so if I know the coordinates of this triangle, I can figure out how they are related to this. Again, I can figure out for simple geometry. But maybe you can just sense the difficulty which may come when the number of joins and links increase. If you talk about a robot manipulated with n links, then it becomes a very difficult problem. It is very cumbersome. The geometry becomes very difficult. Why? Because after a while, because robots are not confined to planes. So after a while, you will find out that the planar geometry is not enough to solve the problem. And okay, so it sounds that we must do something else here, more systematic, to be able to solve this type of problems. And that's why we are going to go into kinematics, because kinematics is the branch of engineering which shows us how to deal with this type of problems. And so far, we haven't been bothered about this. We haven't worried about this because, in our previous occupations or courses, there was no such requirements. But here, when you talk about, there are. Sometimes we may have more than one solutions. Okay, maybe I skipped one thing. Let's see. Okay, given theta 1 and theta 2, just a moment, maybe okay, sorry, I went the wrong way up. Okay, okay, we should talk about this problem as well. This time, in the previous problem, we pressing the wrong buttons. In the previous problem, we said if theta 1 and theta 2 are given, what are x and y? And in the next problem, we are asking if x and y given, what are theta 1 and theta 2? This is a bit more complicated. And this is called inverse kinematics. Why is it more complicated? Because in the previous problem, the direct kinematics problem, there are sines and cosines, whereas here there are inverse sines and inverse cosines. Inverse sines and inverse cosines are a little bit more sophisticated to deal with. And now, in the inverse kinematics, sometimes we end up with more than one solutions. Like this shows, if I want to go, if I am saying, I am at this position, what are the theta 1 and theta 2 values? Is this diagram shows, there may be more than one solutions. And there may even be singular cases. And this is a case of singularity. outcome. Of course, I mean, this may not be very worrisome in a two-dimensional space and with a 2 degree of freedom robot, but you can maybe visualize the difficulties when the robot becomes much more sophisticated. Then we start to talk about dynamics. Dynamics is that, and when we talk about this type of motions, there must be something which actuate these motions. We talked about actuators, actuation. There must be some torques and forces so that this mechanism is going to move. So what type of forces and torques to what magnitudes should we actually apply? Are they going to be the right amount? They should just be the right amount. So how do we calculate these right amounts of torques and forces? And this is the subject of dynamics. So we should also talk about dynamics. And there is inverse dynamics. If I am saying that I am going to give the amounts torque 1 and torque 2, or if the motors we place here at joints apply torque 1 and torque 2, what will be the values of these angles? How much rotation movement are they going to cause? Can we answer this question? And this type of problems are called inverse dynamics problems. Okay, it's time to have a break.